All right, everyone, listen up. Okay, it's week 5. Thank you guys for coming out. We haven't been in person for a while, so I'm glad to have you guys back. Since we don't have a general meeting this week, we're going to go over a few announcements right now just to get everything going. So for the freshman and transfer officer positions, all of the applications already been reviewed. So if you submitted that, that's been reviewed. Interviews will start this week and will end on Sunday. So, and all decisions will be communicated by the beginning of next week. So there's that. Big Little program. If you guys were a part of the Big Little program, thanks for coming out. We just had the kickoff social and that was cool. Make sure to keep meeting up with your groups. And also check your Slack and email for updates regarding all of that. And yeah, let us know if you have any questions about the program through our data science email. So Pacific Life info session, we have an info session with Pacific Life, which is an insurance company based out of Newport Beach, California, scheduled for November 18th from 4 to 5 p.m. Over Zoom. So this will be a good opportunity for you guys to chat with Pacific Life recruiters and ask about job opportunities and internship opportunities. So make sure you attend that, check that out. And we will also be sending out a resume booklet to the recruiters. There will be more info on that later on. This is like a semi-professional event, so make sure you show up or be on video with at least like business casual and come with questions. This is a good opportunity to network, so bring your questions. For the mentorship tip of the week, what are some good courses to take to fulfill major requirements? So these are kind of just like a general list of classes that are very data science oriented. PSTAT 131 is like machine learning, which is a pretty heavy topic for the intermediate pipeline. 134 is called data science. So, and that one's also in Python, so very applicable there too. 135 is big data. And 160A is a little more theoretical. It's applied stochastic processes. So if you're interested, that's a class you might want to take. And there's some other CS classes listed up here too, just in case you didn't know about those already. Sign up info. If you guys haven't already signed up, I assume most of you are already members. Membership fee is 15 and 25 if you want a shirt as well. You can sign up on our website. Also join our Slack. If you haven't already joined the Slack, please join the Slack. All of the important information and announcements are given out through Slack. Yep, and that's it for the announcements. I'll jump right into the pipeline lesson for today. Oh yeah, before I do that, how many of you got a chance to look at last week's notebook? Okay, not many of you, that's okay. Midterms are coming up, I understand. If you guys have any questions about that, I'll be here until 9 after this lesson is done. So if you have any questions about that, let me know. All right, so this week we're going over linear regression. This is really where we start to get into the meat of data science because this is one of the very early machine learning models that we'll explore, and we'll get into that right now. So linear regression is also, in this case, as we're looking at it, known as something called ordinary least squares linear regression, and we'll go over that what that means in a little bit. But essentially, linear regression is a form of supervised machine learning. If you were here for the first lesson, you'll remember that supervised machine learning involves data sets that are labeled. And if you don't remember that, that's cool. We'll go over different types of supervised machine learning next week. And essentially the purpose of linear regression is to predict continuous values as opposed to say like discrete values. Obviously, we're going to be graphing things on a line that's continuous. And the response variable in that case takes on pretty much any value on that line, right? So, and what I mean by ordinary least squares is essentially it's a method. And the method is used for estimating unknown parameters in a model. And we'll go over what those parameters in this model are. But just to reiterate with this pipeline graph that you've been seeing throughout all our lessons, we're kind of in the modeling stage of developing a project right now. And in a way, I could also say, just as easily say that we're kind of in the exploration process as well, only because modeling and exploratory analysis are kind of cyclical in nature. So sometimes you'll come up with a model for something and you'll get to the end of that whole process and you'll realize, wow, my model is trash. It doesn't predict my data set very well at all. And then you're kind of back to the drawing board with your exploratory analysis and you can keep going from there. So yes, unlike linear regression, the process of creating a project and modeling is not very linear, ironically. So just to reiterate what features and labels are, with this example, which is essentially like a housing data set, say you have like a list of houses that have different number of bedrooms associated with them, all sorts of data, things like that would be considered features, right? And in this example, that kind of looks more like a matrix setup of this problem. Each of our values for a specific house, like say this is one house that has 3 bedrooms and 2.5 baths. The features have specific values, as you can see here. The variable that we are trying to predict is the price. And that's considered like our Y value or our response variable or our label, as you would see in this case. So I don't want to make you bore you guys with math or anything, but understanding fundamentally what the equations behind linear regression, are is kind of important. So I'm going to show this to you. As you can see here, let me see if I can get it. Cool. So as you can see here, our dependent variable, in this case, this would be our price. Our price is our dependent variable. You also see it be called things like response to or dependent, that's Y. In this case, our independent variables, or independent variable in this case, are things like these features over here. Things that determine the response are going to be listed as X in this kind of equation. You'll notice that this equation has both a linear component and a random error component. And essentially what that means is with every data set that you have, there's going to be some error component related to it. And in this case, we would denote that with epsilon. So yeah, just to reiterate, Y is our house price, which is listed on our Y-axis for response. And if we're going to look at simple linear regression, which is essentially just using one independent variable and trying to find out where the relationship is between our X and our Y, it's going to look something like this. And this is all something we've seen before. This is, pretty standard, Y equals MX plus B, or at least it appears to be that way. But you'll notice that all the data points on this graph don't conform exactly to the model that we fit for it, which is this line. And the reason that is due to error, right? So every point is going to deviate, if you will, from what we expect. This line here is in a way like our mean or our expectation of what this distribution should be. And the error is the difference between each point and the expectation. The way we figure out what linear estimator is going to be the best for a certain data set is by evaluating with sum of squared error, which is SSE. You'll see it denoted as SSE all the time. If you ever see that, you know what this means. And essentially our goal with creating a linear regression model to fit a certain piece of data is to minimize this function. Okay. For those of you who've never seen this notation before, Y hat, which is sort of this weird symbol with this kind of like up caret here, is what we use to denote like estimation, right? Y in this case is our actual housing prices. Y hat is what we expect it to be. Okay, this is sort of like our prediction. The difference between what we predict and what is actually true is this difference. And obviously, if we're going to try to fit a good model for our data, we want the difference between our points and what we predict to be very small, which is why we do a minimization of the sum. Sigma notation, you've probably seen this before, but that's just the sum of all of these points, the differences of all these points. So total error minimization over our entire data set. So yeah, as you can see here, the distance that's sort of like on this, I guess like perpendicular axis to what our line is, that's our error. You might be wondering why we choose to do squared error instead of just error. And the reason for that is just because it works out mathematically if you don't want to think about it too hard. But really, there are a lot of mathematical properties that go along with squaring the error that work out in our favor when doing calculations, especially with terms to the differentiability of it. I have a question for all of you, and it's okay if you don't really know the answer to this, but who here thinks that this particular data set, this graph, can be accurately modeled using linear regression? Who thinks you can do it? Not very many of you, huh? Well, the answer to this is maybe. And the reason I say that is because at first glance, you would look at this and you're like, well, this isn't a linear. Like there's obviously not a linear correlation between whatever the X and Y of this data set is. It's very clearly like quadratic or something, right? But linear regression is not always strictly linear. And that doesn't really make sense at first, but you'll see in a moment why that is to be true. A lot of the time with our data, there's not a very easy linear explanation for the relationships between the variables, okay? It's very rare that we'll have a data set that's just perfectly linear in terms of two variables, right? But we have this wonderful thing called transformation that we can use to help us model our data sets a little more accurately using linear regression. This is kind of like feature engineering. We're getting into more like data engineering territory here, but that's what it is. Polynomial linear regression is a more complicated version of simple linear regression. And the reason it's still simple and linear, despite the fact that it's very clearly not a line, is because the response variable y is still the result of a summation of the linear component. Right, so there's no like multiplication, like, or any of that kind of stuff in the body of the equation. It's all just sums of terms. And as long as that's true, it's still a linear regression problem. The reason it's still simple linear regression is because we're only using one X variable feature. We'll see what happens in a moment when we decide to introduce more independent variables into the equation. Multiple linear regression is similar, but with more stuff. Okay, so as you'll see here, instead of just having one essentially variable for X, we have multiple now, X1, X2, and so forth, depending on the number of features we want to evaluate. So if we think about our bedroom house example, if we don't want to just predict the price of a house based off of square footage alone, we maybe want to start adding more features in, like number of bedrooms, number of bathrooms, things like that. And as you add more features, you leave the domain of simple linear regression, you move towards multiple linear regression. Does anyone have any questions on that? I don't know if this makes sense. Are you guys familiar with the notation for like this equation? Have you guys seen this before? Okay. So yeah, these are just different visualizations of multiple linear regression. Some examples. In this case, instead of regressing with respect to like 2 dimensions or a single line, we have an entire plane, right? A whole plane that can define ranges of values that our response variable could take. And this one on the right is kind of a combination of both, polynomial and multiple. And the way to determine if your model is appropriately fitting your data is to look at a few different metrics. You've probably heard of R-squared and adjusted R-squared. If you've ever like done experiments in Excel or something, you've probably run into this concept before, but essentially R-squared is just the proportion of your total variance from your dependent variable that can be effectively explained by your independent variables, your x's. Right, and the reason why R-squared wants to be a higher value or closer to 1 is because the higher the number is higher the proportion of your variance that can be effectively explained by your model. Right, adjusted R-squared is just sort of a modified version of R-squared that changes based on the number of predictors in your model. Mean squared error is probably another thing you've seen before. And essentially with this, you'll notice that the equation is actually very similar to sum of squared errors. It's just sum of squared errors averaged over n, which is just essentially the average over n, which is just the number of observations in your data set. You also see this denoted as I sometimes. So if there is anything you take away from learning about linear regression, is that you want to minimize error in any way you can. The distribution of residuals is also another way to tell if your linear regression model is going to be appropriate for your data set. And essentially, you can think of this as like the distribution of your error, right? Remember before we had that random error part of your equation denoted by epsilon. And essentially what that is sort of like the variance that you would experience normally. If you know anything about like Gauss-Markov theorem, your linear model is going to be the best unbiased estimator for your data if your error is homoscedastic. And what that means is there's equal variance throughout all of the error. In this first example, you can see that these error points are pretty evenly distributed around the center line that we have. Right, and that's an example of like a good fitting model. And with respect to the second, we have this sort of like heteroscedastic example where our errors clearly flaring out as we increase the fitted variable. And that's an example where our variance in our error is not constant. And this is just an example of a nonlinear distribution, since it might be hard to tell in here, but we sort of have this kind of curving shape that's going on. We might want to consider moving towards a different model, in this case, something like a polynomial, perhaps. This is just a summary of a few other metrics that we might be using to evaluate whether a model is good or not. I wouldn't pay much attention to Rush-Pagan and Shapiro-Wilks, but it's always good to be familiar with these things. F-test and t-test you've probably encountered before. And essentially with F-test, we're evaluating whether or not the regression model fits the relationship between the independent and dependent variables better than if we just use a simple intercept-only model. And if you'll see here, the intercept-only model is just the response is equal to the intercept, beta naught. T-test is sort of like an evaluation of complexity. So it essentially tells you if each additional parameter in your model adds value to your model. And what that means is by adding more parameters, adding greater complexity to your model, are you actually improving it? Are you actually fitting your data better? Or is it only a hindrance? Is it unnecessary? Links for all of these are, as you know, in the Slack channel. They're also here in the slides, if you look at the slides first or looking at them right now. If you have any questions about the notebook, you can DM me in Slack. You can also ask after lecture this week, next week, anytime. But yeah, that's pretty much it when it comes to linear regression. Definitely take a look at the notebook if you get the chance. I know you guys are all busy, but there's some important information in there regarding scikit-learn. We do a little bit of scikit-learn to go over linear regression in that one, and also sort of a revisitation of data imputation, but a little more complex version of it. So definitely give that a look over. And yeah, that's it for me this week. Like I said, if you have any questions, I'll be here for a little bit after the lesson.